Hello everyone. In this video, we will learn all about continuity and discontinuity of functions. Now, these are examples of continuous graphs. This is a graph of a linear function. This is a graph of a parabolic function. And these are graphs of sine and cosine functions. And this is a graph of a polynomial functions. Now, all of these are continuous graphs. Now, there are conditions that guarantee a graph is a continuous graph. Number one, f of c exists. Number two, the limit of the function as x approaches c exists. And the value for number one and number two are equal. Now, if one of these conditions is not met, the function is said to be discontinuous at x equals c. Now, given these graphs, for example, this is a graph of 3x minus 1. Is the function continuous at x equals 1? By just looking at the graph, our answer here is yes. Next, this is the graph of 3x squared minus 4x plus 1 over x minus 1. Question: is the function continuous at x equals 1? By looking at the graph, our answer here is no. Okay, why not? Because when our x is 1, take note, it is open at 2. So when you say discontinuous graph, at a certain point, there is a gap or there is a hole in the graph. Okay, next. This is a graph of 1 over x. Question: is this function continuous at x equals 0? Now, take note with this graph, at x equals 0, it is asymptotic. Therefore, it is no. Now, another. Is the same graph continuous at x equals 2? So, when you look at x equals 2, there is a value and the limits from left to right is equal. So, therefore, for this, it is yes. Okay, now it's easier to identify the continuity of a function if a graph is given. Now, what if the given is an equation? So, how are you going to do it? For example, is x cubed plus x squared minus 2 continuous at x equals 1? So, with this, we can make use of the three conditions. The first one is we will substitute f of 1. So, substitute 1 cubed plus 1 squared minus 2. Simplifying, we will end up with 0. Now, for letter B, identify the limit of the function as x approaches 1. So, with this, let's substitute and we will end up with 0. Now, take note, the limit of the function as x approaches 1 is equal to f of 1. So, with this function is continuous at x equals 1. Okay, another. Determine if the function x squared minus x minus 2 over x minus 2 is continuous at x equals 0. So, take note, let's solve. For A, let's substitute f of 0. So, substituting x by 0. So, we will end up here with negative 2 by negative 2 or simply positive 1. Okay, letter B, find the limits of the function as x approaches 0. So, substituting this, we will end up with 1. With this, the limit of f of x as x approaches 0 is equal to f of 0. So, with this function is continuous at x equals 0. Now, the same function, identify if it is continuous at x equals 2. Now, with this, let's solve for f of 2. So, substituting, that would be 2 squared minus 2 divided by 2 minus 2. So, simplifying this one, we will end up with 0 over 0, or that is indeterminate. Take note, at this point, the function is discontinuous at x equals 2. Okay, this one. Determine if f of x is x plus 1 if x is lesser than 4, x minus 4 squared plus 3 if x is greater than or equal to 4 is continuous at x equals 4. So, again, step 1 is solve for f of c or f of 4. So, f of 4, belongs to the second function. So x is greater than or equal to 4. So with that, let's substitute. That would be 4 minus 4 squared plus 3, or simplifying, we will end up with 3. Okay, another. Find the limits. The limit of the function as x approaches 4 from the right. So we will make use of the second function from the right. So substituting, we will end up with 3. Another. The limit of the function as x approaches 4 from the left. So from the left, since it's lesser than 4, so we will make use of the first function. So with this, substituting 4 plus 1, we will end up with 5. Now take note, the limit of the function as x approaches 4 from the right is not equal to the limit of the function as x approaches 4 from the left. With this, the limit of the function as x approaches 4 does not exist. So take note of that. Now, given this graph, let's identify whether the function is continuous at certain values of x. At x equals 2, the answer here is yes. At x is equal to negative 3, it is also continuous. At x is equal to 0, our answer here is no. Okay, why no? Because at x is equal to 0, there is a gap of the function. As it approaches 0 from the right, the value is 1. As it approaches 0 from the left, the value is 0. So take note of that. Okay, this one. Identify whether the functions are also continuous at given value of x. Number 1, we have here a quadratic function at x is equal to negative 2. So with this, our answer here is yes. Okay, next, number 2. Still a quadratic function 9x squared minus 1 at x is equal to 1. Our answer here is yes. Number 3. 1 over x minus 2 at x is equal to 2. So take note when you substitute 2 here. So 2 minus 2, that would become 0. And it will make the equation undefined. So therefore, our answer is no. For number 4, if our x is 1, so take note when we substitute 1 here and 1. So 1 minus 1, that would be 0. So 0 over 0, that would become indeterminate. So therefore, our answer is not continuous. Number 5, x is equal to 1. So 1 plus 1, that would be 2. And 1 minus 1, that would be 0. So still, our answer is no, because it will make the equation undefined. Okay, next. For number 6, you have here x squared of x minus 3 at x is equal to 4. When you substitute x by 4, we will end up with 1. So therefore, our answer is yes. Number 7, at x is equal to 8. So 4 minus 8, that would become negative 4. So take note, never take the root of a negative radicand. So therefore, it's no. And for number 8, our x here is 0, so it will make the denominator 0. So still, our answer is not continuous. So take note of that. Okay, let's have this. Continuity on an interval. Take note, a function is said to be continuous from the left if f of c is equal to the limit of f of x as x approaches from the left. And a function is also continuous from the right if f of c is equal to the limit of the function as x approaches c from the right. Now take note, for polynomial functions, they are continuous everywhere. The absolute function is also continuous everywhere. Rational functions are continuous on their respective domains. So take note here, never divide by 0. Then for the last, the square root function is also continuous if the value for the domain starts from 0 until positive infinity. So take note for this, never take the square root of a negative radicand. Okay, let's have an example. So given this graph, by just looking at this, is it continuous from negative 1 until 1? Our answer here is yes. What about from negative infinity until 0? It's still yes. And from 0 until positive infinity, it's still yes. Okay, now given this graph, identify whether the following intervals are continuous. For number 1, from negative 1 until 1, our answer here is no. Okay, why not? Because take note, at x is equal to 0, our graph here is open. Next, what about from 0 until 1? Our answer here is yes. So take note of this. Okay, why yes? Because take note here, this is parentheses 0. So it means you start from the number after 0. So 0 is an excluded value. So take note of that. Next, for number 3, from negative 1 until 0, and take note 0 here is bracket. So when you see bracket, 0 is already part of the value. It is included. So with this, for number 3, our answer is no. Because again, at x is equal to 0, it is open here. Okay, next. What about from 0.5 until 2? Bracket, our answer here is yes. Okay, now, determine whether the following function is continuous on the given interval. So, take note, this is x squared plus x minus 2 from negative infinity until positive infinity. Now, take note, this is a graph of a polynomial functions and it is continuous everywhere. So, therefore, our answer here is yes. Okay. This one, determine whether the following function is continuous on the given interval. This is a function of the square root of 9 minus x squared starting from negative 3 until 3. Now take note, when you graph 9 minus x squared, square root of 9 minus x squared, you will get this graph from negative 3 until 3. So take note, with this, f of x is negative 3. These are our endpoints. So f of negative 3, so substituting here, we'll end up with 0. F of 3, so substitute, still we will end up with 0. So next, let's find the limits. So the limit of negative 3, as it approaches from the right, so substituting will end up with 0. Next, the other end is the limit of the function as it approaches 3 from the left. So substituting will end up with 0. So with this, the values for a and b, it's equal. So it is continuous from the right of negative 3. The other one, it's also equal. So it's also continuous from the left of 3. So with this, the function is continuous from negative 3 until positive 3. So take note of that. Now, given this, identify the largest interval over which the function, the square root of x plus 2, is continuous. Now, take note, this is square root. Take note, never take the square root of a negative radicand. So that it will never be negative. So therefore, our value here should be greater than or equal to 0. So x plus 2 should be greater than or equal to 0. And simplifying this, our x should be greater than or equal to negative 2. Now, writing this in notation form, that would be, or ordered pair form, that would be negative 2 bracket until positive infinity. So graphing this, x plus 2, the square root of x plus 2, this is our graph. So it starts from negative 2 until positive infinity. Now, based on this graph, are the following intervals continuous? From negative 5 until positive 3, our answer here is no. So take note, you only start at negative 2. What about from 7 until 10 bracket? Our answer is yes. What about from negative 3 until negative 2 bracket? Our answer is no. Okay, take note of that. Another, identify the largest interval over the function x over x squared minus 1. Now with this is a rational function. Take note, for rational functions, never divide by 0. So therefore, our denominator here x squared minus 1 should never be equal to 0. So solving this, we will have x squared should never be 1. Getting the square root to both sides, so our x here should never be positive or negative 1. Or writing this in ordered pair form, that should be any numbers except negative and positive 1. Now take note, when you sketch this, x over x squared minus 1, you will get this graph. So take note of this. Now, based from the given, identify whether the following intervals are continuous. From negative 5 until negative 3, from negative 5 until negative 3, it is continuous. What about from 0 until 10 bracket? Our answer here is no. So take note, at x equals 1, it is broken. No. Okay, what about from negative 3 until negative 2? The answer here is yes. So take note of that. Okay, now given this, consider the given functions. So actually, it's a function with 4 functions in it. It is x if x is lesser than or equal to 0. It will be 3 if our x is greater than 0 but lesser than or equal to 1. Our function is 3 minus x squared if our x is greater than 1 but lesser than or equal to 4. And the function is x minus 3 if our x is greater than 4. Now, to do this, let's identify its ordered pairs. Now, there are 4 functions, so we will have 4 ordered pairs or 4 table of values as well. So lesser than 0, so that would be 0, negative 1, negative 2. So take note, whatever is our x, that's the same value for our x, for our y here. So with this will be our first TOV. Now for the second TOV, it will start from 0 until 1. Start from 0 until 1, but 0 is excluded. So with this, the value for our y is 3. So this will be our TOV. Now for the third, it will start from 1 until 4, but 1 is excluded. So if our x is 1, so that would be 3 minus 1, you will get 2. If our x is 2, so that would be 3 minus 4, you will get negative 1. If our x is 3, so 3 minus 9, you'll get negative 6. And if it's 4, 3 minus 16, that's negative 13. And for the last table of values, that should be values for x greater than 4. So 4 is excluded. So 4 minus 3, it's 1. So take note, the red marks here indicates these are excluded values. Then 5 minus 3 will get 2. 6 minus 3 will get 3, and so on. Now, sketching this will be our graph. Now, graph for the first TOV, this is our graph. This is included to the left. This is open, then close. This will be for second graph, in which our value for y is 3. For the third graph, it will start from 1 until 4. So 1 is open, and at 4 it is closed, and this is quadratic because it is squared. Then for the fourth graph, it will start from 4 until positive infinity, but 4 is open. For 5, we will get 2. Then for 6, we'll get 3, and so on. Now, given this, these are our TOVs. This is the corresponding graph. Now, let's identify if these intervals are continuous. From 0 until 1, but 0 is open or excluded, our answer is yes. From 0 until 1, but 0 is already included, our answer here is no. Now, from 4 until positive infinity, but 4 is excluded, so right after 4, our answer is yes. But from 4, including 4 until positive infinity, our answer is no, because we have here open and we have here closed at the bottom. Then from 1 until 4, and it is included, our answer here is no, because at 1, there is a gap. Then from negative infinity until 0 open, our answer here is yes. So take note of this one. Okay, types of discontinuity. Now, there are three kinds of discontinuity of functions. The first one is removable discontinuity. So when you say removable discontinuity, there is a hole somewhere in the graph. Next is a jump discontinuity. So when you see jump discontinuity, there are limits as it approaches a certain value of c from the right and from the left, but they are of different values. So there is a gap. Then the third kind of discontinuity of function is infinite discontinuity. So meaning at least one of the functions is infinite or asymptotic. Take note of that. Now this is an example of a removable discontinuity. F of x is equal to x squared minus 4 over x minus 2 if our x is not equal to 2. Now, substituting f of 2 here, so that would be 2 squared minus 4 over 2 minus 2. This will become indeterminate. So with this, the function is discontinuous at x is equal to 2. Now solving for this, we can simplify this as x minus 2, x plus 2 over x minus 2. We can cancel x minus 2, so we're left with x plus 2. Now getting the table of values here, if our x is 0, so we'll have 0 plus 2, it's 2. If our x is 2, so this will be indeterminate. Or when we substitute to the simplified form, we'll have 4. If our x is 3, so 3 plus 2 is 5. 4 plus 2 will get 6. Now graphing this one, the graph of this function is this one. Now take note, it is open at x is equal to 2. Now take note, when you say removable discontinuity, the discontinuity of it can be removed using redefinition. So again, to remove the discontinuity of removable discontinuity, we need to redefine the function. Now take note, with the given original function, x squared minus 4 over x minus 2, if our x is not equal to 2. So by the time that x is already 2, we need to replace y as 4 so that it will become continuous graph. So with this, when we sketch this, so instead of an open circle here, this will be closed because again, we redefine it. Okay, another example. G of x is equal to 3x squared minus 4x plus 1 over x minus 1 if x is not equal to 1. Now, if x is equal to 1, the value for y is 1. So again, getting g of 1 here, let's substitute and simplifying, we will have 0 over 0. So therefore, this function is discontinuous at x equals 1. Now simplifying this one, we can factor the numerator as 3x minus 1 times x minus 1. We cancel this, so we're left with 3x minus 1. Now getting the table of values here, if our x is 0, so that would be negative 1. If our x is 1, so again, it's indeterminate. If our x is 2, so that would be 5. If our x is 3, it will become 8. Now graphing this function, we will get this one. So take note, it is open at x equals 1. But it is, at x equals 1, it is 1 based on the given here. So again, we can remove its discontinuity by redefining it. So by redefinition, this will be our new graph. So instead of 1, we should have 2. So the new equation then would be g of x is equal to the given function if our x is not equal to 1. But if our x is 1, our y should be 2. So this is the new redefinition of this function. Okay, next. Jump discontinuity. So from the word jump, there is a gap between the two functions. So given this, f of x is equal to 3x minus 2 if our x is lesser than 3, and x minus 1 if our x is greater than or equal to 3. So with this, we will solve for f of 3. So f of 3 belongs to the second function. So that's why it's 3 minus 1. So simply it is 2. Now getting the limit as 3 approaches 3 from the right. So that would be making use of function 2 from the right. So substituting, we will end up with 2. Another, finding the limit of the function as x approaches 3 from the left. So from the left, so lesser, so we will make use of function 1. So substituting this one, we will end up with 7. So take note, the limit of the function as it approaches 3 from the right is not equal to the limit of the function as it approaches 3 from the left. So with this, the limit of the function as it approaches 3 does not exist. So then, the function is discontinuous at x equals 3. So making use of the TOV for the first graph lesser than 3, but 3 is excluded. So substitute 3 times 3, that's 9, minus 2 will get 7. If our x is 2, so 3 times 2, it's 6, minus 2 will get 4. If it's 1, so 3 minus 2 will get 1. If it's 0, it will become negative 2. Now for the second set of TOV, that will be for the second function. So start from 3 to the right, so increasing. So 3 is included. So 3 minus 1 will get 2, 4 minus 1 will get 3, and so on. So with this, graphing this will be our graph. So this is the graph of the first function. So take note, it is open here. It's shaded going down. And x minus 1, so start from 3 to at 4, 3, 5, 4, and so on. This will be our graph. So take note, for jump continuity, the limits from left and right exist, but they are not equal. So jump discontinuity cannot be redefined. So take note of that. Given h of x is equal to x plus 1 if x is lesser than 4, and quantity x minus 4 squared plus 3 if our x is greater than or equal to 4. Now getting the value for h of 4, so we will make use of the second function. So that would be 4 minus 4 squared plus 3. So simplifying, we'll end up with 3. Next, finding the limits of the function as x approaches 4 from the right, so meaning greater than, so that would be function 2. So with this, simplifying, we will end up with 3. Now, next, getting the limit of the function as x approaches 4 from the left, so meaning lesser than, so that would be function 1. So 4 plus 1, so that would be 5. Now take note, the limit of the function as it approaches 4 from the right is not equal to the limit of the function as it approaches 4 from the left. So with this, the limit of the function does not exist. So with this, the function is discontinuous at x equals 4. Now, making use of the TOV, so for the first function, that would be lesser than 4. So 4, 3, 2 until infinity. So if our x is 4, that would be 5. If our x is 3, so 3 plus 1 is 4. If our x is 2, so 2 plus 1 will get 3. Now for the second TOV, this will be numbers that are greater than or equal to 4. So start from 4 until infinity. So if it's 4, so 4 minus 4, that's 0 plus 3, that would be 3. If our x is 5, so 5 minus 4, that would be 1. 1 squared plus 3, that would be 4. If our x is 6, so 6 minus 4, that would be 2 squared, that would be 4 plus 3, will have 7. Graphing this will be our graph. So for x plus 1, this is our graph. And for x minus 4 squared plus 3, this will be our graph. So again, the limits from left and right exist, but they are of different values. So this is a jump discontinuity. Okay, next. Infinite discontinuity. So given the function f of x is equal to 3 over x minus 2. So let's solve for f of 2. So this will become undefined. So with this, the first condition does not satisfy already the conditions So with this, the function is discontinuous at x equals 2. So making use of the table of values, so 2 here is undefined. So to the left of 2, so -1. So if we'll substitute -1 here, we'll have -1. If we will substitute with 0, that would be -1.5. If we'll substitute with 1, that would be -3. 1.5, so that's between 1 and 2, we'll get -6. If it's 2, that will be undefined. Now, to the right, as finding the limits of the function as it approaches 2 from the right, so suppose we'll get 5 here. So 5 minus 2 will get 3, so we'll end up with 1. If our x is 4, so 4 minus 2, that would be 2 or 1.5. If our x is 3, so 3 minus 1, that would be 1, so we'll end up with 3. If our x is 2.5, so 3 divided by 0.5 will get 6. So if it's 2, that will be undefined. So graphing this, we will get this. Now to the left, so take note at x equals 2, it is asymptotic. So take note of that. So to the left, we have here 1 and -3. We have 0 and -1.5. We have -1 and -1. So just connect. This will be our graph. So for the other side, if our x is 5, our y is 1. If our x is 4, that would be 1.5. If our x is 3, it's 3. If our x is 2.5, that would be 6. So connecting, this will be our graph. So take note, for discontinuity case 2, the limits does not exist because it is infinite. So take note of that. Okay, another example, the limit of 1 over x, as long as x is not equal to 0. So with that, f of 0, so it's undefined. So the first condition is not satisfied, thus the function is discontinuous at x equals 0. Now finding the limits as our x approaches 0 from the left, so we can have -3, -2, -1, -0.5 until 0. If it's 0, it's undefined. If it's -3, that's -1/3. If it's -2, that's -1/2. So -1. So if it's -0.5, so it's -2. Now, finding the limits as x approaches 0 from the right, so we can have 3 to 1.5, then 0. So with this will be our value. So graphing this, so take note, the graph is asymptotic at x equals 0. So x is -2, so it's -0.5. If our x is -1, it's -1. If our x is -0.5, we'll get -2. So connecting, this will be our graph. Now for the other side, if our x is 2, our y is 0.5. If our x is 1, our y is 1. If our x is 0.5, our x is 2. So connecting, this will be our graph. So again, the limits does not exist because it is infinite. Okay, this one. For each function wherein the graph is given, identify the type of discontinuity given. Remedy any removable discontinuity with an appropriate redefinition. So given this graph, y is equal to f of x. So take note, there is a hole somewhere here. So therefore, this is an example of a removable discontinuity. Redefining this, so we will have f of x is equal to f of x if our x is not equal to 0. Now, if our x is equal to 0, the value for our y should be positive 2 so that this will become shaded. Take note of that. Another. This is g of x, so with this, it is an infinite graph. Another, this is a graph of h of x, so take note, there is a gap at x equals 1, so this is an example of a jump discontinuity. Okay, next. Okay, so identify the different discontinuities here and identify their types. If removable, state the redefinition. Okay, so for number 1, at this point, this is removable. At this point, it's also removable. At this point here, it is jump. At this point, at x equal to 1, it is also jump. At x is equal to 3, it is infinite. And at x is equal to 5, this is removable. So for removable graphs or discontinuity, we will redefine it. So for the first one, this is f of x at x equals negative 2. So the value for y here should be positive 2 so that it will be shaded here. Now for the second graph, for the second removable discontinuity, our redefinition here would be y is 3.5 if our x is negative 1/2. So take note of that. Then for the last, our redefinition here would be positive 5 if our x is 5. So take note of that. Okay, now this is an example of a tricycle fare in a city. Now making use of piecewise function. So the tricycle fare in a certain city is 10 pesos for the first kilometer. Every additional kilometer, an additional 2 pesos is added to the fare. So for example, if the first kilometer is traveled, so that's 10 pesos. By the time the travel distance is already 2 kilometers, so therefore the fare in the tricycle will be 2 pesos. So again, traveling further at 3 kilometers, that would become 14 and so on. So making use of the TOV, 1 kilometer, it's 10 pesos. 1.5, it's still 10 pesos. 1.9 kilometers, still 10 pesos. By the time it's already 2 kilometers, the fare is 12 pesos. By the time it's 3 kilometers, it's 14 pesos. 4 kilometers, 16 pesos, and so on. So this is an example of a piecewise function. Okay, another. This one. Let's have this sample problem. You have a summer job that pays time and a half for overtime if you work for more than 40 hours. After that, it is 1.5 times your hourly rate of 300 pesos. Now write and graph the function that gives your weekly pay in terms of the number of hours you work. How much will you make if you work for 50 hours? Now take note, if you work for 1 hour, your pay is 300 pesos. If you work for 2 hours, your pay is 600 pesos. If you work for 40 hours, your total payment is 12,000 pesos. Now take note, after or more than 40 hours, your rate will become 1.5 already. So, for example, if you will work for 41 hours, your total pay will be 12,450 pesos. So, how come it's like this? Because every hour after 40, your rate is already 300 times 1.5, which is already 450 pesos. So, if you work for 42 hours, so that would be 450 times 2, that will be 12,900 pesos. So take note, how was this done? So again, 300 for the first 40 hours. Then after 40 hours, your rate for the hours after 40, your rate is already 1.5. So with this, let's simplify. So 300 times 40 is 12,000. 1.5 times 300 is 450. So distribute, that would be 450 each. 450 times negative 40, that's negative 18,000. So final answer here is 450 each minus 6,000 pesos. So with this, your function here would be the payment is 300x. If your time is less than or equal to 40 hours, but your rate will be 450x minus 6,000 if you work more than 40 hours. So, what if you will work for 50 hours? So, with this, we'll make use of the second function. So, 450 times 50 minus 6,000. So, your rate by then is 16,500 pesos. So graphing this is the graph. So take note, I just skip it. So at 30, or so at 40, you will get 12,000. But at 41, it's already 12,450. By the time it's already 50 hours, you will get 16,500 pesos. So take note, this is an example of a real-life situation involving piecewise functions. Okay, so that would be all about continuity and discontinuity of functions.